X. Hello everyone, welcome again to Cabinda example. We are going to conduct a shock response of a motherboard using COMSOL Multiphysics. So we'll investigate the effect of 50-gram half-sine shock load with a duration of 11 milliseconds on a computer motherboard. We'll use two methods to do this. We'll use the response spectrum analysis and direct time stepping with mode superposition. In terms of material, generic PCB will be applied on the board. For the heatsink, we'll use aluminum. The chips, silicon of course. The connectors, we'll use plastic. Capacitors are made of different type of materials, so therefore we would apply some effective material properties to those. In terms of constraints, we'll apply a fixed constraint on all 6 mounting holes. In other words, we'll fix the motherboard to a chassis. And in terms of load, for the spectrum analysis, we'll use the pseudo acceleration spectrum. And all parts of the motherboard are subjected to transient body load, in other words, gravity load. And this has a magnitude of 50 grams, and as mentioned before, a duration of 11 milliseconds during the transient computation. And we have our formula, and we'll use this in the load factor input field when we get there. Now let's jump over to COMSOL Multiphysics and get this done. COMSOL Multiphysics is loaded and ready for us. So let's begin our simulation by going to the model wizard. So let's select that, 3D. Let's go down to structural mechanics, solid mechanics. Let's add that. Now let's add a study. And under preset studies for selected physics interfaces, let's add a response spectrum. So once you click that, let's select done. Now let's import our geometry. So in the home toolbar, let's select import. Let's browse to our geometry. And now let's select import, and our geometry is imported. And now what I don't like is these grids, so I'm going to take off those grids. So let's take that off. Now let's navigate to our model builder, and in geometry we also have form union, which is directly under our import. So if we select form union, and for the action it is currently set as form a union, we're going to change that to form an assembly, and then select or click build all. Now let's go to our definitions toolbar, select explicit, and we're going to add the PCB. So we can select it here. The geometry is simple. For certain things you can select directly, and let's change the name to PCB. Okay, now let's add more explicit definitions, and this time we're going to add heatsink. So let's use the selection list this time. It will be much easier for us to just come here, select 17 and 21, so we know those are our heat sinks, and select add, and here we need to type heat sinks. Okay, so we give that a label. Now we go back to our model builder. We have our heat sinks here. So if we select PCB, that is our PCB, that is our heat sinks. Okay, so we'll add more explicit definitions. We're going to define our entire model. So let's add another one, and this time let's call this one chips, and Let's navigate to our selection list and let's select domains 3, use Control 4, 7, 8, 9, 10, 18, and 22. So if we go to the XY view, you can see we have our chips here. Okay, and we need to add those. Let's go back to our model builder, and we need to now add our connector blocks. So let's go ahead and do such. So let's go to explicit again. Let's call this one connector blocks, and let's go to our selection list, and let's select 2, 5, 6, 11, right up to 14, and select add. And let's go back to our model builder. Now let's add our capacitors. Okay, so explicit, and let's give it a name. Let's call this one capacitors larger. Let's go to our selection list, and we're going to select 23 all the way to 25 and 28 and also 31. So these are our larger capacitors here, and let's add those. What we can do here is right click and duplicate. Let's change the name here. Let's just call this one smaller. Okay, you can come here and hit this to clear, and then go to our selection list, and we're going to add our smaller capacitors. So those are 15, 16, 19, 20, 26, 27, 29, and also 30. Add those and go back to our model builder. Now let's define our mounting holes. So let's go to explicit once more. Let's call this mounting holes. Let's change this from domain to boundary. Let's go to list, and now let's select all our boundaries. Now with all those selected, let's just double check what we have selected before we click add. So we have 6, 8, 10 to 13, 15 to 18, 24 and 26, 28 all the way up to 35, 40 and 42, 44 to 47, and 49 to 52. That looks good. Let's hit add. And yeah, okay, so it's the inner portion of the hole or the holes, and not the recess or counter bore. It's just the inner part. Okay, so let's go back to our default view, and let's go to model builder, and let's navigate to, well, just above our geometry there's an icon here that says view. Let's click on it, and let's go over to the colors section. So let's expand that, and we need to select the show material and material color and texture. Okay, let's navigate to the home toolbar. Let's select add material. Before we go any further, let's close our definition. Let's close our geometry, and let's close solid mechanics for now. Keep everything neat, also study. Okay, so let us go to our add material window that we've opened, and we'll use the built-in material function. and let's look for FR4 circuit board. So it's right here, so let's select that, add to component. Remember previously we were selecting our components and defining them. Well, this is one of the reasons why. We can now go to selection and we can just simply select PCB. Okay, so the FR4 circuit board is only applied to the PCB. Let's go to our material window again, and right in built-in, we are still working in built-in. Let's select aluminum and add to component, and for the aluminum all we need to do is go to our selection, and this time we want to add our heat sinks. Now we need to add our silicon. Silicon is also in built-in, so let's scroll down, let's select silicon, add to component, and for the silicon that will be the chips. So all we need to do is go to selection and select chips. Okay, now we need to add a material to the connector blocks. Therefore, let's navigate to acrylic plastic. Let's add to component, and let's choose connector blocks. Let's navigate down to appearance. So here we have appearance, and where we have material type, let's change that to plastic shiny right here, and for the color let's change that to black. Okay, let's navigate back to built-in. Let's add aluminum, let's add to component. Now we have to manipulate this because cylindrical capacitors have a complex internal structure with several layers of different materials. So we need to use some form of effective material manipulation for this. We would need to give it a new name. So let's call it capacitors larger composite material. And of course, for the selection, we would need to select the capacitors larger, and we need to do some manipulation to the density value. So here, let's manipulate this to 1500. Let me bring this a little bit larger so you can see clearly. So we'll manipulate the value, just the value for the density. Okay, now we need to go down to appearance, and for the material type here, let's change that to plastic shiny. Okay, and the color, we're going to change the color to yellow. Okay, that looks good. Let me just go to a plan view here so you can see what we were manipulating. So it's the larger capacitors. Now we're going to do similar for the smaller capacitors. So let's navigate back to our add material window, and let's add another aluminum, add to component, and this time we'll choose the capacitors smaller, and let's manipulate our density value, but this time let's just change the 7 to a 0 and make that 2000. Okay, and for the appearance, let's scroll down, let's expand appearance, and let's change this from aluminum to plastic shiny. And the color, let's make that cyan or anything of your choice. Let's change the name, okay, because we manipulated the aluminum material to create our own. And let's click on add material to close the window. Let's bring this back a bit smaller. We can go to our default view. Now let's add the fixed constraint to the mounting holes. In our model builder, let's go to our physics, so you can just select solid mechanics. Now let's right click and let's select fixed constraint. For this selection, let's choose our mounting holes. Let's navigate to our physics toolbar where we have pairs. Let's select continuity. Let's select this little plus button here, add. So make sure you have pair selection expanded. So if it's closed, you expand it, add. And to select all of these, you can just select the first one, scroll down, use shift, select the last, and then select OK. Let's save our file and add our mesh. Let's navigate to mesh. Let's right click on that and let's add a size. In our geometric entity level, let's choose domain, and for the selection list, let's select our capacitors smaller. For the predefined, let's use fine. Okay, now let's add a free quarter. So we can do that by simply navigating to our mesh toolbar where we have boundary. We can select free quarter, and we need to select quite a bit of boundaries. So let's go ahead to our selection list and select those. Now let's double check our selection. So we have 4, 7, 9, 25, 27, 41, 43, 146, and 202. Let's go back to our model builder and let's add a size to our free quad. So let's right click on free quad and add size. For the geometric entity level, let's select boundary. Let's select boundary. And for the selection, let's select all boundaries. Now let's go down to our element size, and we're going to change it from predefined to custom. By the way, let's go back to predefined and let's choose extremely fine, and let's go down to our custom, and for the maximum element size, let's select that and let's change the 6 to a 5, so it's 0.005. And let's go down to the minimum. Let's select the box and leave the minimum as default. let's navigate to boundary and select mapped, and let's go to our selection list, and we're going to select the boundaries that we need. So let's double check what we selected. So we have 46, 52, 57, 62, 69, 74, 79, 88, 93, 100, 106, 111, 118, and we should have 174, and also 238. So let's add those. You can turn on transparency to have clearer visual of our motherboard components. Let's go back to the border builder, and let's right click on mapped, and let's add size. So in terms of size, let's choose all boundaries. Okay, so geometric entity level, boundary selection, all boundaries. So that's it for the mapped. Now let's go to the mesh toolbar. When we are still in the mesh toolbar, let's click on swept, and let's right click on the swept one, and let's select distribution. Okay, let's now manipulate our distribution. Let's call it distribution default. So let's call it distribution default. Number of elements, we'll make that 3. Okay, so let's go back to swept 1 again, and let's add another distribution, and let's call this distribution PCB. Okay, and in terms of selection, we only need the PCB, and for the number of elements, let's key in 2. Okay, so we're going to continue with our distribution. What I'm going to do, I'm just going to right click on distribution PCB, and then I'm going to duplicate that, and we're going to call this distribution heatsink or heat sinks. And for the number of elements, we're going to select our key in 4, and of course we will need to change our selection from PCB to heat sinks. Okay, and now let's select our, click on build all to build our mesh. We have an error. What do? We can panic and start all over, or we can just simmer down, read our error, and then fix it. So it says a problem occurred when building mesh feature swept 1. So if you reach it, you can see at the bottom it says, or the final one, it says internal error in FreeQuad measure. So let's just click OK. Let's navigate to our FreeQuad. Okay, and let's come to our geometric entity level, and if you notice, we have nothing selected. So make sure you have in geometric entity level, make sure you select boundary, and for the selection we're going to select our boundaries. Okay, so we need to select 4, 7, 9, 25, 27, 41, 43, 146. I think we selected these before, but we did not add them. Okay, so we need to look for 146. Should be here. And also 202. So yeah, I can recall we selecting these, but we did not add them, so we need to add those. Okay, go back to our builder, and we can just select build all in our window, and it will redo our mesh, and we fixed our error. So when there are errors, don't panic, just try and solve them. Okay, so let's continue. Now to see our mesh clearly, let's take off transparency. Let's click on mesh, and here is our mesh. Now let's minimize these, and let's go to our home toolbar, and let's go to functions. Under global, let's click interpolation, and we're going to edit this. Firstly, let's change the name of it. Okay, so for the name, let's input this. Let me bring it bigger. It's actually acceleration grams versus frequency hertz. Okay, now let's navigate down to load from file, and we'll import our text file. So navigate to where you have yours stored and click open, and here is it. Now let's go back to our functions, and under global, let's select analytic, and let's manipulate this. So for the name or label, let's call it vertical spectrum, and for the function name, VSP, let's make that lowercase. Okay, and for the arguments, let's just type, well, sharper frequency. Okay, and for the expression, let's input an expression here, which is you're going to integrate the frequency multiplied by the grams constant. Okay, and in terms of the units for arguments, let's enter hertz, and for function, let's enter meters per second squared. And in terms of the plot parameters, for the lower limit, let's enter 5, and the upper limit, let's enter 600. Okay, and now let's select create plot. For the label, let's call it vertical spectrum, and in terms of the x-axis label, let's select that, the y as well, and for the x, let's call it frequency hertz. Okay, so frequency hertz, and for the y, let's call it pseudo acceleration, and we'll put the units behind that as well, meters per second square. Let's go down to the axis, and let's select manual axis limits, and for the x minimum, let's enter 0. The x maximum, let's enter 600, and in terms of the y and the y minimum and y maximum, we'll leave it as default, and let's just hit plot. Okay, so here is our plot. Let's go to 1D plot group and change the name to vertical spectrum. Let's go down to plot settings, and let's select x-axis label. Also, let's check the y-axis label. For the x-axis label, let's call that frequency hertz, and for the y-axis label, let's call it pseudo acceleration, meters per second square. Now let's go down to axis. Let's select the manual axis limits. X minimum 0, X maximum 600, and leave the Y minimum and Y maximum as default, and let's hit plot. Now let's conduct our study. So let's close results. Let's go up to study 1. Let's expand that. Let's click on step 1, eigenfrequency. Let's change the eigenfrequency search method to manual. Desired number of eigenfrequencies. Let's select a checkbox, and also let's select the checkbox for search for eigenfrequencies around. So for the desired eigenfrequencies, let's change that to 15, and the search eigenfrequencies around, let's change that to 65. And let's go to our home toolbar and click compute. Let us navigate to the participation factors, and let's select table graph. This shows the participation factors for vertical translation for all computed eigenmodes, but we only need the participation factor normalize Z translation. So let's go ahead and do that. So let's navigate to our table graph settings, and we're going to manipulate the data. So plot columns, let's change it to manual, and now we can select the participation factor normalize Z translation, and let's go down to our coloring and style, and inside here for the line markers, let's change it to asterisk. For line, let's change it to dotted or anything of your choice. Let's scroll down a little bit, and for the positioning, let's change it from interpolated to in data points. Let's navigate back to 1D plot group 3, and let's change the name to participation factors. Let's navigate to our vertical spectrum, and let's adjust the axis limits. So for the X minimum, let's change that to 30. For the X maximum, let's change that to 400, and for the Y minimum, 500. For the Y maximum, 850. And let's scroll down to the legend, and let's choose middle right. Okay, and let's right click on vertical spectrum. Let's select global, and for the data sets, let's choose study 1. For the Y axis data, let's click replace expression. Let's come to global definitions, functions, and let's select VSP frequency, vertical spectrum. Double click on that. Now let's go down to our X axis data, and where we have parameter. Let's change the parameter from solution number to expression, and for the expression let's just type FREQ, which is frequency for short, and let's go down to the coloring and style. So let's expand that, and here for the line let's select none. For the markers let's select cycle, and for the positioning let's select in data points, and let's expand legend, and let's change it from automatic to manual, and let's key in values at eigen frequencies. Okay, and let's hit plot. Let's go to our model builder and select mode shape solid here, and in the settings let's locate the data, and let's choose 72.526. That's for the eigen frequency, and let's hit plot. Let's go to our default. This shows our third eigen mode. So if you want, you can actually go through here and plot some of these. If you want to plot the second, you can go ahead and do that. Just select the second one and hit plot, but let's just stick with the third one because it has the maximum participation factor for vertical translation. That's the reason why we'll stick with the third one, and it's also close to the maximum of the shock spectrum input. Okay, let's navigate to our results toolbar, and let's go to global evaluation. Navigate to the replace expression, and under component 1 let's choose definition. Let's scroll down to response spectrum 1. Let's expand that, and let's expand effective modal mass, and let's choose the C translation. So let's double click on this one, and for the expression we're going to manipulate this a little bit, and we're going to key in this expression. I'm going to make this bigger so you can see exactly what is it. Let's go down to data series operation, and in operation let's expand this. Let's choose integral. Let's scroll down a bit, and for the method let's select summation, and let's scroll back up, and where we have evaluate, let's expand this and choose new table. So this value shows that the computed eigenmodes account for more than 94% of the total mass. Now let's add this special data set for response spectrum evaluation. Now let's go over to our model builder. Let's just minimize data sets. I have mine expanded. Right click on it, and let's scroll down to where it says more 3D datasets, and let's go over here, select the last one, response spectrum 3D. Let's navigate to spectra, and down to vertical spectrum. Let's expand list and let's select vertical spectrum VSP. Now let's go to our results toolbar, but it's already open for us, and let's go over to 3D plot group, and let's change the name of this plot group to maximum displacement response spectrum, and let's go down to the data section and the dataset section right here. Let's change it from study 1 solution 1 to response spectrum 3D1. Let's go over to the maximum displacement response spectrum in our model builder. Let's right click on it and let's select surface. Inside the settings for our surface expression, let's change this and let's key in W and let's hit plot. Let's minimize this a little bit, this as well. Let's go to default, and this actually shows the vertical displacement as a result of the response spectrum evaluation. This concludes the response spectrum analysis method. Now let's navigate back to our physics, our solid mechanical physics, and we'll perform a transient analysis of the structure response under a body load in the form of a half-sine pulse with 11 milliseconds duration and 50 grams magnitude. So let's go ahead and do that. Firstly, let's minimize some of these things. So let's minimize our results, minimize our study for now. Let's expand component 1. Let's expand solid mechanics. Let's navigate to our physics toolbar, domains, under volume forces. Let's choose gravity. And for the selection, let's choose all domains. Now we're going to use a time dependent modal solver to compute the transient response by representing the solution as a superposition of pre-computed eigenmodes. So we'll need to add a new study for this. Let's go to our home toolbar. Let's click on add study, empty study, add study. Click add study here to close it. Let's clear generate default plots, leave everything else as is, and let's select time dependent modal under our study steps, and let's change the range. So you can key in those range, and let's change the time units to milliseconds. Let's go back to our study toolbar. Let's click on show default solver. Let's expand solution 2. Let's click on modal solver 1. So for our relative tolerance, let's make that 0.0001. So 0.001. And for the damping ratio is 0.005. But actually 0.05. Yeah, that's better. and we need to click on advance, and in our introduction we mentioned the equation for the load factor, so we're going to key in that equation. Okay, and let's expand output. Let's scroll down. This part is very important because if we have to store all of our derivatives, it's going to take a very long time, and also it's going to need a lot of space to store all these. Okay, so what we are going to do, we're going to clear this checkbox, and then we can scroll down and just touch on this load factor for a few seconds, so it actually multiplies all the apply loads, including the gravity load. Okay, so those are the important areas or points in this modal solver. Now let's go home, or we can just click on compute here, or if you go home you can click on compute here. So it doesn't really matter, but I'll do it from the study. And we have an error, so we need to make some adjustments. So as I mentioned before, finding the solution for it. So let's go back to modal solver 1, and let's choose solution. For the solution, it's none. We cannot leave that as none. Okay, so let's select solution 1, and now let's compute our study again. So we solve our error and compute our second study. So let's close this study 2 window and expand results. Okay, now let's navigate to our home toolbar, and where it says a plot group, let's select 3D plot group. Let's call it maximum displacement time history, and now let's locate the data section and select study 2 for the data sets. Let's right click on maximum displacement time history. Let's choose surface. In the expression for the surface settings, let's key in this equation here, and let's click on the maximum time displacement or maximum displacement time history, and in the 3D plot group settings, let's go down to the title. We're going to expand that, and we're going to choose manual, and let's just add some spaces between, and let's go down to the parameter indicator. Let's delete what's inside of that and leave it blank, and also let's go to our plot, hit that, go to default view, let's go back home, and let's add another 3D plot group. This time we're going to call it displacement time. Okay, let's change the data sets to solution 2, and the time we'll change it to 11 milliseconds, and let's right click on displacement time. Let's choose surface, and for the expression let's key in W. Let's right click on the surface one right here. Let's choose deformation, and let's go down to our scale factor. Let's select this box. Let's key in 1 here, and let's go plot. Let's go to our default view. Now let's animate our solution. Model builder look a bit nasty, so let's close the data sets. Let's close our derived values, vertical spectrum. Let's close everything that's opened. Much better. Now so we can close our solid mechanics or global definitions. Keep everything tidy. Okay, so let's go to our results and expand animation, and let's select player. So let's navigate to scene, subject, and let's choose displacement time. Let's go down to the number of frames and let's key in 100, and let's click on show frame. It will take a couple of seconds to generate such. Now let's right click on animation and select play, and you can see our solution is now being animated from 0 to 50 milliseconds. In our results toolbar, let's select 3D plot group. Let's call this stress response spectrum. For the data sets, let's call it, I'll choose the response spectrum 3D 1. Let's scroll down, make sure everything is alright. Okay, let's right click on stress response spectrum. Let's select surface, and for the surface let's call this solid nieces. Okay, and for the range, expand range. If yours is closed, just need to expand it like that. Manual color range, leave the minimum as is, and for the maximum that will be 150 million. Okay, and let's hit plot. Let's go to the XY view, and as you can see, around our memory chip shows extremely high stress levels. We can now minimize this, and you can go ahead and analyze all of your plots, your solutions. Okay, and you can simply come here and change the views and analyze your solutions. This concludes our simulation the shock response of a motherboard. Thank you for watching. Bye for now.